In this lecture, we'll cover Chapter 9, Liquids and Solids. One thing that distinguishes liquids and solids from gases that we studied in the previous chapter is that the particles, the molecules or atoms or ions of a liquid or a solid are much closer together than they are in a gas phase. And therefore, those particles experience forces of attraction between them. For molecules, we call them intermolecular forces. There's four basic types of intermolecular forces. The first are called London or dispersion forces. These are the weakest of all attractive forces, and they exist for all molecules. The next are the dipole-dipole forces of attraction. These are stronger than London dispersion forces, and they exist only for polar molecules. The next one is called hydrogen bonding. This is an intermolecular type of attraction between molecules, and it exists for polar molecules that have an OH group, NH group, or an FH group as part of the molecule. And the fourth one are called ionic forces. These are the strongest of the four, and they only exist for ionic compounds or salts, and it's the attraction between the positive and the negative ions in the crystal lattice. So we'll talk about each attractive force individually, starting with the London dispersion forces. These are weak attractive forces between all molecules, and they happen because of small instantaneous dipoles from the electron clouds of neighboring atoms being distorted. And so when these instantaneous dipoles develop, they're stronger when you have a larger electron cloud, and therefore increasing atomic size or atomic mass will lead to stronger London forces. In this picture, we see illustrated London forces. So again, when the electron clouds of neighboring atoms or molecules get close together, they induce a distortion in the electron cloud, which results in temporary positive and negative charges on opposite sides of the molecule. And because of this, neighboring molecules are now attracted to each other. Of course, opposite charges are attracted, so the positive of one molecule is attracted to the negative of others. These charges disperse and only last for an instant, and so therefore the attractive forces are very weak. Okay, we have a table of data, and we're looking at the noble gases going from helium, the smallest at the top, all the way down to xenon, the largest noble gas. And we're looking at freezing point, and note that freezing point and melting point are the same thing, just difference in the direction that you're going. If you're going solid to liquid, we call it melting point. Liquid to solid, we call it freezing point. Okay, so what do we see? We see that the freezing points are increasing as molecular size increases. And therefore, this is happening as a result of the London forces getting stronger. The stronger the attractive forces between molecules, the more heat energy is required to break those attractive forces. And so now we see a physical property, freezing point, that changes as a result of these intermolecular attractive forces changing. Dipole-dipole intermolecular forces of attraction occur for polar molecules. As we see in the diagram, polar molecules are those that have a permanent dipole. One side of the molecule has more electron charge, the other side has less, and therefore we have a negative and a positive, partial positive charge on either side of the molecule. And when two or more molecules come together, the opposite charges, the positive end of one molecule is attracted to the negative end of the other. Note that these are partial charges, not full charges like we would see in salts. Now, hydrogen bonding is even stronger than dipole-dipole attractions, and it exists between polar molecules that have fluorine, oxygen, or nitrogen attached to a hydrogen atom. The hydrogen atom in that bond is the partial positive charged atom, and then the electronegative atom is the partial negative charged atom. This one is the strongest, and therefore it'll require more energy to break hydrogen bonds than it takes to break a dipole-dipole attraction, and the dipole-dipole attraction is stronger than the London dispersion attraction. In this diagram, we see the network of hydrogen bonding that exists for water. So every hydrogen atom being partially positive will be attracted to an oxygen atom on a neighboring molecule, and so on and so forth. So it forms a very extensive network and makes the water molecules have a very strong attractive force between them. The first thing that we want to be able to do with these attractive forces is to look at a molecule and state what types of intermolecular forces would be present for that molecule. In order to do so, we need to know whether the molecule is polar, nonpolar. If it's polar, we need to know whether or not it has OH, NH, or FH in the molecule. Once we know that, we can identify the intermolecular forces. Let's start with silicon tetrahydride, SiH4. We would start by drawing the Lewis structure, and it would look very similar to methane. There's a silicon atom in the middle with 4 single bonds to 4 hydrogen atoms. When we look at the 3D electron pair geometry, it winds up being tetrahedral. Since there are no lone pairs on the central atom, the geometry as well as the electron pair arrangement is also tetrahedral. This is a symmetrical geometry, and therefore we would conclude that SiH4 is a nonpolar molecule, perfectly symmetrical. Since it is nonpolar, the only attractive intermolecular force we have is London dispersion forces. Let's look at another example. Here we see the molecule CH3, CH2, CH2OH. This molecule is clearly not going to be symmetrical, and therefore we would conclude that it is polar. In addition, it has an OH group, so it's polar with an OH group. That means it can participate in hydrogen bonding. So this particular molecule will have hydrogen bonding. It will also have dipole-dipole attractions, and all molecules will have London dispersion forces. So therefore, all 3 intermolecular forces are present for molecules in this sample. We should also be able to compare 2 molecules and determine which one would have the stronger of the 2 intermolecular forces of attraction. We'll start with chlorine and fluorine. Both are diatomic nonpolar molecules. When you're comparing nonpolar molecules, they both would have London dispersion forces. Which one would have stronger dispersion forces? It would be the larger molecule, the one with the higher molecular weight, and that one would be chlorine. Next, we see CH3CH3 and then CH3OH. Big difference here. The one with the OH is polar, and it also can have hydrogen bonding because of the OH. The one on the left is nonpolar, and so therefore the one on the right will have stronger intermolecular forces of attraction. Next, we have 2 molecules with oxygen atoms in them. However, the one on the left has an OH group capable of hydrogen bonding. The one on the right, the oxygen is not connected to a hydrogen, and therefore, even though the one on the right is polar, it can't hydrogen bond, And so the molecule on the left has the stronger intermolecular forces of attraction. The last two that we need to compare are carbon dioxide and sulfur dioxide. If you actually go about drawing the Lewis structures of these, you will find that carbon dioxide is linear and nonpolar. Sulfur dioxide ends up with a lone pair on the sulfur, and so it has a bent geometry and therefore is polar. In addition, sulfur dioxide is a larger molecule, so not only will it have dipole-dipole attractions that carbon dioxide does not have, but it also will have stronger London forces of attraction. So for both reasons, the sulfur dioxide is going to have higher or stronger intermolecular forces of attraction. This graph illustrates one of the interesting effects of hydrogen bonding. So we're looking at a series of molecules with each different colored line, and the central atom is in a different group of the periodic table. Let's start at the bottom with the blue line. So the four molecules we have are CH4, SiH4, GeH4, and SnH4. So these are group 14 or 4A central atoms, and we're moving down as we go to the right. We're moving down on the periodic table. And therefore the molecules are getting larger. And what do we see happening with boiling point? Boiling point increases as molecular size increases because the London forces of attraction increase. However, what we see on the remaining three lines is that the molecule on the left, which would be the smallest molecule, does not have the lowest boiling point like it did for group 4A or group 14. Why is that? Well, for group 15, nitrogen being the central atom in NH3 means that we have an NH group that is capable of hydrogen bonding. And you see the fact that hydrogen bonding is there, that gives our NH3 molecule a higher than expected boiling point based on just its molecular size. Same thing happens with the group 16, H2O, and then H2S, H2SE, etc. The water has a higher boiling point than expected, and the same thing happens with the group 17 central atoms. So, in general, if you're just looking at nonpolar molecules, as molecular size increases, so do intermolecular forces of attraction, and therefore boiling points increase. But when you introduce hydrogen bonding, because that's such a strong intermolecular force of attraction, it makes the boiling points higher than expected based only on molecular size. And so this graph shows quite nicely the significant impacts of hydrogen bonding on the observed properties of molecules. In addition to boiling points and melting points, we can look at some other properties and correlate them with intermolecular forces of attraction. Those will include surface tension, capillary action, viscosity, and vapor pressure. Surface tension is the resistance of a liquid to increasing its surface area. Water will form a perfect sphere when it falls in order to minimize surface area. The stronger the intermolecular forces, the higher the surface tension. Capillary action is the ability of a liquid to flow into narrow spaces, often against external forces like gravity. We can see that happening in the diagram on the upper right. We have a pool of liquid at the bottom, and we have very skinny tubing made of glass, and we see the water moving up against gravity. So why does that happen? The water is attracted to the inner walls of the tube. The glass is a polar surface, water is polar, and so like things are attracted to one another. As the film moves along the surface of the glass in the upward direction, surface area starts to increase. This increases surface tension. In order to counteract that, the water column in the middle is then going to move up to decrease surface area so that surface tension is minimized. When the liquid is attracted to the glass, the curvature is concave. That's what we see in water, and that's called a meniscus. And remember when we learned how to measure volume in glassware, we would always measure at the bottom of that meniscus. That only happens when water is attracted to the surface. If I were to have the water in a plastic container, you would not see a meniscus. Or if you had a liquid that was nonpolar, like mercury liquid, you would not have that upside down curvature. As you can see, you have more of a flat surface with mercury. So looking at the diagrams at the bottom, which one represents water and which represents mercury? So the one on the left is mercury, the one on the right is water. Viscosity is the resistance to flow exhibited by liquids and gases. When I think of viscosity, I think of honey or syrup. These are liquids with high viscosity, and you see how when you pour those liquids out of the container, they pour very slowly. There's a resistance to flow. Looking at the molecules at the bottom, which do you expect to be more viscous, water or glycerol? Well, when you look at those structures, water only has one OH group. Glycerol has 3 OH groups. So I would expect glycerol to have a higher extent of hydrogen bonding between its molecules and therefore have a stronger hydrogen bonding and therefore higher viscosity. One way that viscosity can be measured is to take a column of a liquid and drop a steel ball into the liquid and measure the amount of time that it takes the steel ball to fall from the top to the bottom of the liquid. And looking at this figure, we have either water or glycerol on the left, either water or glycerol on the right. Well, on the left, the steel ball reached the bottom much more quickly than the right. So then I am going to conclude that on the right we have glycerol and on the left we have water. Another property that relates to intermolecular forces of attraction is vapor pressure. And before we get to vapor pressure, let's just briefly review the different states of matter and the transitions between them. As you know, we have solids, liquids, and gases. And typically, when you're comparing a substance's different states of matter, the solid is the most dense, followed by the liquid, and then the gas would be the least dense. Now, for water, we find that water actually has a higher density in the liquid state than in the solid state. But for most other substances, the opposite is true. So solids and liquids will differ from gases in terms of density, in that solids typically have higher density than liquid, but both solids and liquids have much higher density than gases. Compressibility would be the opposite. Gases, having such a low density and the particles are spread out so much, they are more easily compressed. Gases have a higher compressibility than liquids, and liquids are higher than solids. Rigidity, how rigid something is. Solids are obviously the most rigid, followed by liquids, followed by gases. Kinetic energy follows the trend of compressibility. The gases will have the highest kinetic energy, then liquids, then the solids. The transitions that occur between these states are essentially where the substance is changing from one state to another, and each transition has its own unique name. Solid to liquid is called melting. Another term for melting is fusion. And then liquid to gas is vaporization. Gas back to liquid is condensation, sometimes called liquefaction. Liquid to solid is freezing. Sometimes we skip the liquid state and we go from solid to gas, that's sublimation, or gas back to solid, that's deposition. Make sure you're familiar with each of these phase transitions. In terms of absorption of heat or emission of heat, when you're going up, in other words, from left to right on the diagram, those are endothermic transitions. When you're going from right to left on the diagram, those are exothermic transitions. Let's look at a few examples. Identify the phase transition occurring in each. Mothballs slowly becoming smaller and eventually disappearing, that would be sublimation. They're not melting. You don't see a pool of liquid. They just simply disappear. They're going from solid straight to gas. Rubbing alcohol spilled on the hands feels cool as the volume of liquid decreases. So the liquid is evaporating. That's evaporation. Raindrops hit a cold metal surface and it becomes covered with ice. So the liquid water in the raindrops turning to solid water or ice, of course, that's freezing. Candle wax turning to liquid under the heat of the candle flame, melting. So back to vapor pressure. What exactly is vapor pressure? We mainly will look at vapor pressure for liquids. And so this would be the partial pressure of the vapor over the liquid. And we measure it once that vapor over the liquid comes to equilibrium. And it will come to equilibrium at a different pressure depending on the temperature that we're holding the liquid at. So we can see in the graph below that we start with a liquid in a closed container. Some of the liquid molecules will escape into the vapor phase, and at that point, the vapor pressure begins to increase. At a certain point in time, the vapor pressure becomes constant with time, and we now have an equilibrium between the liquid and the gas states in that closed container. Vapor pressures will vary with temperature, and they will vary with different substances. For different substances, they are impacted by the strength of the intermolecular forces. The stronger the intermolecular forces, the more tightly held the liquid molecules are together, and the more difficult it is for them to escape into the vapor phase, creating vapor pressure. So the stronger the forces in the liquid, the lower the vapor pressure. So looking at the diagram shown on the right, we have 4 different substances, starting with diethyl ether on the left, followed by chloroform and carbon tetrachloride, and then finally water on the right. So as we go left to right, what we're seeing is that vapor pressure for a given substance at a given temperature is lower. So let's say we were looking at 40 degrees Celsius. We would see water at 40 degrees Celsius has the lowest vapor pressure, then chloroform, then carbon tetrachloride, then diethyl ether. And water is the only one of these 4 substances that has hydrogen bonding, the strongest intermolecular force of attraction. So what we see here is that the stronger the intermolecular force of attraction, the lower the vapor pressure. And why is that? Why does vapor pressure decrease when attractive forces increase? It's because the stronger or more tightly held the liquid molecules are, the fewer of them escape into the vapor phase. So there's an inverse relationship between the strength of the intermolecular attraction and vapor pressure. The second thing that we can determine from this graph is the impact of temperature on vapor pressure. And what do we see happening? Let's just look at water. As we increase the temperature of water, what is happening to the dependent variable, the vapor pressure? It's increasing. So when you put more thermal energy into a sample of liquid, more of the molecules are going to acquire enough energy to escape into the vapor phase, to actually vaporize. So the higher the temperature, more molecules go into the vapor phase, and therefore higher the vapor pressure. Practically speaking, the vapor pressure of liquids is what allows you to smell a liquid. You're not actually sensing the liquid state molecules, you're sensing the molecules from the liquid that escaped into the vapor phase. And so when you smell a liquid, you are basically sensing the vapor pressure of the liquid. Liquids that have stronger smells probably have a higher vapor pressure. Liquids with weaker smells probably have a lower vapor pressure. It turns out that boiling point and vapor pressure are related to one another. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid equals external pressure. And when those two pressures are equal, we start to see vapor bubbles forming within the liquid, and that's what we call an active boil. There's a term called normal boiling point. This means the boiling point of the liquid when the external pressure is exactly 1 atmosphere. So if you ever hear the term normal boiling point, That's referring to the boiling point at 1 atmosphere. And it just so happens that if you live at a higher elevation, you're experiencing lower than 1 atmosphere of external pressure. And so the boiling point that you measure is going to be a little bit lower than the normal boiling point. External pressure increases, the boiling point will also increase. If the external pressure decreases, the boiling point will decrease. On this table, we can see the boiling point of water at many different external pressures. And what we're doing is changing elevation in order to change the external pressure. So the lower the elevation, the higher the pressure. When you're exactly at sea level, like New York City, New York, you are at 760 torr or 1 atmosphere. If you're below sea level, like in Death Valley, California, you would have higher pressure, 770 millimeters of mercury. As we move up in elevation to the top of Mount Washington in New Hampshire, we have an atmospheric pressure of about 590, and water is going to boil at 93 degrees there. If you go up even higher to the top of Mount Everest, the atmospheric pressure is only 240 millimeters of mercury, and your boiling point of water is just 70 degrees. So from what we've discussed so far, the strength of the intermolecular attractions between molecules impacts various properties of liquids such as vapor pressure, surface tension, and viscosity. And looking at the table at the bottom of this page, we see that as London forces increase, vapor pressure decreases, but surface tension and viscosity increase. And this is the case except for substances that can hydrogen bond, like water and glycerol. They are going to have much stronger forces of attraction than other molecules of the same size, and therefore their properties will not follow the exact same trend as the others. ALO 9.3, which of the following compounds would have the highest boiling point? So we need to scan the list, we need to compare molecular size, and we also need to look for the presence of OH groups which can hydrogen bond. So the largest two molecules are the second one and the fourth one. They differ in that the fourth one has an OH group, the second one does not. Therefore, I'm going to say that the last one is the one that would have the highest boiling point because it has the strongest intermolecular forces. ALO 9.5, use the following vapor pressure data to answer these questions. In which liquid are the intermolecular attractive forces the weakest? So for vapor pressure, weaker intermolecular attractive forces leads to higher vapor pressure. So which of these two has higher vapor pressure? Well, we have same vapor pressure but different temperatures. And so the one with the lower temperature to achieve the same vapor pressure would have the weaker intermolecular attractive forces. That would be the second one, the C2H5Br. If we looked at the vapor pressure of the first liquid, C8H18, at 21 degrees Celsius, how would that compare to 400 torr? Would it be higher or lower than 400 torr? Well, at 104 degrees Celsius, it equals 400 torr. If we lower the temperature, the vapor pressure will be lower. As temperature decreases, so does vapor pressure. Now we're going to look at physical properties of liquids and solids. For solids, we have a property known as the heat of fusion, delta H FUS. This is the enthalpy or the heat required to melt a solid, and it's measured in kilojoules per mole. When you're at the melting point, temperature will remain constant until all of the solid has turned into liquid. If you were to reverse that process and go from liquid to solid, now we're talking about freezing. The same quantity of heat would be required. However, the sign of that process would change. So whereas melting is an endothermic process with a positive delta H, freezing is an exothermic process or a negative delta H. The reaction for the fusion process would take a substance such as water in the solid state, and it would react, or it would change into water in the liquid state. Notice that's not a chemical reaction, that's just a physical change. And the heat of fusion of water is known to be 6.01 kilojoules per mole. That is, 6.01 kilojoules of heat are required to melt 1 mole of water. We're going to compare that to the heat of vaporization of 1 mole of water, and we'll see how the magnitude changes. So liquids will have their own heat of vaporization. The heat of vaporization is the heat required to vaporize 1 mole of liquid, and it's measured in kilojoules per mole. At the boiling point, the temperature of the liquid will remain constant until all of the liquid has evaporated. If you change that process and instead of vaporizing, you condense, you go from gas to liquid, the quantity of heat will be the same, but now heat will be evolved until we'll have a negative delta H of condensation, positive delta H of vaporization. So for water, we would represent that process as H2O liquid transforming into H2O gas. And the delta H of vaporization for water is positive 40.7 kilojoules per mole. Comparing that to the previous slide, the heat of fusion of water, that value is around 6 kilojoules per mole. So we see that vaporizing water requires more than 6 times more heat than melting water. Why is it that the heat of fusion of water is lower than the heat of vaporization? Well, the heat of fusion, as you remember, is the heat required to melt a solid. The heat of vaporization is the heat required to evaporate a liquid. Melting a solid will cause the particles that were locked in place to now slide and move around freely, but they're not significantly separated from one another when you melt a solid. Evaporating a liquid causes the particles to move much faster and also separates them completely from one another, breaking all intermolecular forces of attraction. This process obviously requires a lot more energy than melting, and that's why the delta H's of vaporization are always higher than the delta H's of fusion. In OWL 10.10, you're given some basic information about a sample, and you are going to be asked to calculate a delta H for a certain process and a certain quantity of sample undergoing that process. So here we're dealing with cobalt. We have its boiling point, its melting point, its delta H of vaporization, and its delta H of fusion. We also have the specific heat, which is the amount of energy that is required to change the temperature for the solid as well as for the liquid. So we may need to use all or just some of the information in the table, so we have to pay attention to what we're being asked for. In this one, we're asked for the delta H in kilojoules for the process of freezing, not melting, 30 grams, not 1 mole, of liquid cobalt, and we are at the melting point. So with this one, we don't need to worry about the specific heat because we're not changing the temperature within the liquid or the solid. We're right at the melting point. Also, we need to recognize that freezing is the reverse process of melting. So while the magnitude will be the same, the sign will change. And so the delta H of freezing is going to be negative 15.5 kilojoules per mole. And while that's for 1 mole, we're trying to calculate it for 30 grams. We need to convert those moles to grams by dividing by molar mass. And then we need to multiply by 30 to make it, instead of 1 gram, it'll be for 30 grams. And when we run through that calculation, we get negative 7.89 kilojoules. In these next couple of slides, we're going to look a little more closely at the relationship between vapor pressure and temperature. As I mentioned before, as you increase temperature, vapor pressure for any one substance will also increase. But we see that the relationship here is not linear. We have an exponential relationship between these variables. If we're to change the plot, And now take the natural log of pressure on the y-axis and use reciprocal temperature on the x-axis, we end up getting a linear relationship between these forms of the variables. And so, like with any linear plot, we can use the y equals mx plus b format. So y being the natural log of pressure, mx, so x is 1 over temperature, and the slope of the line, m, is delta H of vaporization. We can derive what's called the Clausius-Clapeyron equation. The most common form of this equation that we'll be using is the two-point form of the equation. So we now have the natural log of P2 over P1, and then instead of just 1 over T, we have in parentheses 1 over T1 minus 1 over T2, and then the slope is now the delta H of vaporization divided by R, the ideal gas constant. So this is a very handy equation when you're looking at a substance, and we have essentially 5 variables that we're looking at. We have 2 temperatures, 2 vapor pressures, and then the 5th variable, the heat of vaporization. So in these problems, I recommend that you summarize your data. So the data that we're given in this problem is as follows. The first pressure is 400 millimeters of mercury. For the Clausius-Clapeyron equation, the units of pressure can be any units of pressure. So just use the units that were provided in the problem. So the first pressure, 400 millimeters of mercury. The first temperature, 2,330 Kelvin. The delta H of vaporization, positive 202 kilojoules per mole. And then we're asked for the vapor pressure at a second temperature. We don't know what that second pressure is. That's our unknown variable. The second temperature, 2,360 Kelvin. And then R. So since we are using the delta H of vaporization in kilojoules per mole, we'll just divide R by 1,000 and make it 0.0083145 kilojoules per Kelvin mole. Now that we have our data summarized, we're going to write out the equation. The ln of P2 over P1 is equal to delta H of vaporization over R times 1 over T1 minus 1 over T2. I did want to make a note here that in OWL, this equation is sometimes written as follows. Okay, the left side is the same, the right side is different. They put a negative sign in front of the delta H of vaporization over R, and then they flip the temperatures. It's now 1 over T2 minus 1 over T1. Is this equation in green mathematically different than the equation in red? No, they're exactly the same. We've just simply multiplied the term outside the parentheses and inside. They've each been multiplied by a negative. So when you make that operation twice, essentially you're not changing the math of the problem. I prefer to use the formula at the top because there's no negative sign in the front of the variable. But either one of those will work, and mathematically they're the same. So once you write out your equation, you then want to substitute the known variables and leave your unknown variable, P2, and you'll solve for P2. Okay, so also we want to look and make sure that our units are canceling out as they should, and all of the units on the right cancel out, which means our pressure will be in millimeters of mercury. So on the right, we'll take 202 divided by 0.0083145, and that ratio will get multiplied by 1 over 2330 minus 1 over 2360. Once we get the result for all the numbers on the right, which ends up being 0.13255, to get rid of the natural log function on the left, we're going to take e to the power of both sides. When you take e to the power of a natural log, those two operators cancel one another out, and so we end up with P2 over 400 millimeters of mercury equals 1.1417. P2 equals 457 millimeters of mercury. Let's do a reality check. Does that answer make sense? Well, the second temperature was higher than the first temperature. So should the second pressure be higher or lower than the first pressure? It should be higher. As you increase temperature, the vapor pressure of a liquid also increases. So that answer does make sense. Let's try another problem. Here we're asked to calculate the heat of vaporization of a liquid, given that the vapor pressure of the liquid at 25 and 50 degrees are 43.9 and 93.7 millimeters of mercury, respectively. We're going to summarize the data. Note the temperatures need to be converted to Kelvin. For this formula, temperature has to be in Kelvin. Write out your Clausius-Clapeyron equation. Plug in the given variables and the unknown variable into that equation. And notice here the unknown variable is delta H. Cancel out units that cancel out. Solve the terms on both sides of the equation. Rearrange and solve for delta H. And delta H ends up equaling positive 24.3 kilojoules per mole. And so we want to do a reality check on that answer. Does it make sense? For enthalpies of vaporization, they're typically between 1 and 100 kilojoules per mole. This does fall into that range, so therefore we say it does make sense. If you'd like some more help with these types of problems, check out the video linked in the lecture notes. The last topic we're going to cover in this chapter is phase diagrams. What is a phase diagram? A phase diagram is a graphical way to summarize the conditions under which the different states of a substance are stable. And so the different states of the substance are going to be solid, liquid, gas, and then we have a fourth state of matter called supercritical fluids. Each region, the indicated state is stable, and on the lines we'll have two states in equilibrium. For example, there will be a line between solid and liquid. That is the melting line, okay? And so solid and liquid are in equilibrium along that line. Then we have a line between liquid and gas. That is the vaporization line, and liquid and gas are in equilibrium right on that line. And there's a third line between solid and gas, and that is the sublimation line. There will be a point on the graph where all three curves intersect, and that is called the triple point. And then finally, if you go above what's called the critical point, and it's that upper point between liquid and gas, you will have a supercritical fluid. Here is the phase diagram for carbon dioxide, and you can see what we're plotting is pressure on the y-axis, temperature on the x-axis. As you move left to right across the diagram, we go solid, liquid, gas. And as I mentioned before, the line between solid and gas is the sublimation line. The line between solid and liquid is the melting line. Between liquid and gas, the vaporization line. On those lines, two states of matter are in equilibrium. The final point on the graph is the critical point. And we can see the critical point for carbon dioxide is 31 degrees Celsius and 73 atmospheres. Above this pressure and temperature, you won't have a liquid, you won't have a gas, you'll have a supercritical fluid. You should be able to look at a phase diagram and draw some basic conclusions from it. For example, using the carbon dioxide phase diagram we were just looking at, let's try to answer these questions. Ambient pressure and temperature, what do we mean by that? Ambient pressure is about 1 atmosphere. Ambient temperature is like room temperature, and it's about 25 degrees Celsius. So what state of matter is carbon dioxide in at that temperature and at that pressure? Well, from the diagram, we see that carbon dioxide is a gas at ambient pressure and temperature. What about negative 78 degrees Celsius and greater than 1 atmosphere? What state of matter will carbon dioxide be? And at those two values, it'll actually be a solid. It's what we refer to as dry ice. If we start at negative 78 degrees Celsius and a little higher than 1 atmosphere, what will happen if we increase the temperature? Well, what will happen is we're moving left to right across the diagram. We see the solid is going to turn straight into a gas. That is called sublimation. At that point, what happens if pressure and temperature increase? Well, it depends on where you're starting on the diagram, but in general, it will convert into a solid, liquid, or a supercritical fluid. Another feature of the phase diagram is the slant of the melting curve. So with the carbon dioxide phase diagram, if we look at the line between solid and liquid, it slants to the right. And so the reason for that is as we are increasing pressure, the melting point will also increase. So that will cause it to slant to the right. And the melting point will increase at higher pressure because when you think about it, under higher pressure, the molecules are getting pushed closer together. If they're closer together, it's going to take more energy to break them apart and melt that solid. The water phase diagram, though, appears to have an anomaly. The melting curve, the line between A and B, is actually slanted to the left and not the right. Well, I'll give you a clue. Earlier I said water is a unique substance. It doesn't behave like a lot of other substances. For most substances, the solid state is more dense than the liquid state. Water is an exception to that trend. As pressure increases, melting point decreases because the molecules are actually closer together in the liquid state than in the solid state. So if you increase pressure, you're pushing the molecules together and you're now favoring the liquid, not the solid. And that's why that curve goes to the left and not the right as it normally does. I'd like to talk a little bit more about supercritical fluids. I told you earlier that a supercritical fluid will exist above the critical point. And so the critical point is the temperature and pressure where if you go above that, the liquid state can no longer exist and the substance becomes a supercritical fluid. You can see in this diagram as we move from A to B to C. In A, we clearly have a liquid at the bottom and a gas at the top. In B, we still have liquid at the bottom and gas at the top, but there's a phase in between that's sort of an intermediate phase. When we go to C, we've increased the temperature enough now. We're above that critical point, and the only phase that's in there is the supercritical fluid. OWL 9.9. Refer to the following phase diagram, not drawn to scale, for neon and answer these questions. At a pressure of 1 atmosphere, the temperature, 24.5 Kelvin, is called the what of neon? So I'll move along the graph. I find 1 atmosphere on the y-axis, and then I move to the right until I get to 24.5. 24.5 Kelvin and 1 atmosphere, you are sitting right on the melting curve, the line between solid on the left and liquid on the right. So when you're right on that line, you are at the melting point of neon, right? Okay, what is the normal boiling point? Remember that term, normal boiling point. Normal boiling point is the boiling point at 1 atmosphere. And on a phase diagram, the boiling point occurs when you are between between liquid and gas. So for neon, that's going to fall at 27.1 Kelvin. The triple point is sort of the center of this wishbone-looking graph, and this looks like it occurs at 0.425 atmospheres and 24.4 Kelvin. Critical point, if we move up into the right at that tip top between liquid and gas, this occurs at 26.2 atmospheres and 44.4 Kelvin. This concludes the major topics that we're covering in Chapter 9, and this is also the last chapter that we'll cover in this semester of General Chem 1. If you have any questions on the topics that were covered in this chapter, don't hesitate to ask. Thank you.